No, we're given a plane there, and we're given a vector, a point, so basically that's a picture. We're given a plane and we're given a point. We need to find the distance from the point down to the plane. I chose a rather general way to look at that question. So the actual statement of the question is down here, not here. Here will be some further consideration. So we're given this plane. That's the vector equation of the plane on page 18. Vectors and everything. And where's my B vector? And that's the B vector, if I'm not mistaken. Yes. So here's my B vector or B point. This is a point with a position vector B. Here's my plane. Did I give a name here? Here's my plane. So we have the vector A. I still don't have it. Okay. All right. Let me just take it through you. It's a little bit convoluted presentation, but it's worth it, I think. Again, this is the setting of the question on page 18. We're given a plane and we're given a vector. We need to find the distance from the tip of that vector. I didn't picture the vector itself. I just picture the tip of that vector. Don't be confused with that. Down to the plane. The plane has two directional vectors. Here they are. I didn't give any names to this because probably we won't be needing these names. So this is the two vectors, but they pictured here, these blue ones. And this is the A vector. Again, the A vector is not shown on the picture, but the tip, the end point, is shown. That's this dot. Right, so before we do this question in this particular form, I'll try to address this problem of finding the distance from a point to a plane in rather general setting. But for that, I would need the Cartesian equation of the plane rather than the vector equation. When we just finished our general considerations and we will come up with the formula, analytical formula for the distance, we will apply this formula to this plane. But before we can do that, we will convert this plane to the Cartesian form. And we know how to do it. We just did it twice, two different ways. But we will do it later. I'll start my general considerations with the plane which is given in the point normal form, like this. Later on, for this particular plane, we will find this form rather quickly with the cross product. We will do that. But we don't need this for now. So we're given a normal to the plane. We're given this A vector. Here's my normal. We're given the plane, we're given the position vector, we're given the normal. That's the equation of the plane. We can, of course, you can open it up. I mean, you can open all of the brackets. You can simplify things. You can find the equation in this form, in this, like a canonical Cartesian equation of the plane, where A, B, C will be the components of n vector. This d coefficient will be some algebraic arithmetic manipulations with these components of A and components of n. Now, what I will do now, look at this, what I'm going to do. I'm going to run I'm going to run a line through this B point, like this. So I'll take L will be the line with this vector equation. Look at this. That's the line which gets to the point, for the tip of the vector B, parallel to my normal vector. That's the line perpendicular to my plane, isn't it? Here it is. And of course, the distance we're after, if I take the intersection point, plane, the distance will be this distance. So all I have to do in principle, I have to look at these two equations of the plane and the line, try to find this intersection point, and when I can do that, I can find the distance after that, right? So what I will do now is this. Look at this. I'll take this vector form in order to come up with some general analytical formula for this distance, and we will succeed in that in 5 minutes. I will take this vector equation of my line, and I will put it in here, right in the position of this x, and I'll try to manipulate with the result of that and see what that will give me. Okay, let's just try to do that. So by the way, the n vector, remember this is a normal vector, so the components of my n vector, here they are, A, B, C. That's the coefficients here, coefficients of this Cartesian form. So here's what I'm going to do. Look at this. I take this right hand side, and I plug in here in the position of this x. That's the result of that. N dot product. This is my x. This is a sub for x. Take A equals 0. Now, with the dot product, we can do lots of things like with numbers. So what I'm going to do, I'm going to expand this. If I expand this, and if I do some manipulations with that, look what will happen. I'm saying it will be lambda times the length of the vector the length of the vector n squared. This is this n dot product with this term, and all of the other terms I took them on the other side. Actually, I didn't really expand it. I just kept it in the way it was. So B take A dot product with n, and negative because they went to the right hand side. That's how it is. Now I can solve for lambda, because remember, we need to point x naught. This point x naught, if you're looking for this point, you need to find the value of the parameter which corresponds to that point x naught. And that's the value of the parameter. I have to just solve for lambda here in these very general terms, right? My lambda is, if I solve for that, negative this one, almost extra shift. That's my solution for lambda. This is the value of my parameter in the very general terms, which will correspond to this intersection point. Now I can take this value and put it back, because we're after the point, right? We're after the point because we need the distance. I can take this value, I can put it in here in the position of this lambda, and then I can find the value for my x. Let's just do that. And actually I call this x naught, this intersection point, the position vector for the intersection point. And here it is, b negative, because lambda is negative, is my x naught point. Now we can raise the question about the distance. Here it is. Distance, it's the length of the vector b take x naught. If I sub in my x naught expression in this formula, of course b will cancel b. All what will be left is this piece. So we will have n dot product with b a and length of n. Well, because when you put the absolute value around it, of course this is just a number which come out of the absolute value. So this absolute value, or the length of the vector, will be just around this n, and one absolute value here will cancel this square. That's why you have only one n. Although there is a mistake here. Who sees the mistake? Thank you very much. The absolute value is missing here, because when you take the number out of the length, it must come in the absolute value. Nobody says this product is positive, so actually there must be an absolute value. Of course, you don't have to confuse this vertical bars with this vertical bars. This vertical bars in the numerator, this is the numerical absolute value, the one we do on numbers. The vertical bars in the denominator, these are the length of the vector. Same identical notation, but conceptually totally different things. Right. Now, look what I'm going to say now. When you look at this expression, this one, the one which sits under the absolute value, what is it? I mean, like in the context of what we're just discussing right now, can you just alternatively describe it for me? Look at the point normal equation of the plane, and look at this. This is just the left-hand side of the point normal equation of the plane, which is effectively, this is just the Cartesian equation of the plane, like this. This one under the absolute value, this is just this expression where x is replaced with b, and the b is something we know. So actually this thing in the numerator, this is just left-hand side of this Cartesian equation where x, y, and z replaced with the components of the b vector. If I call the components of the b vector x1, y1, and z1, I can now write the distance like this. A numerator, this is a result of subbing these components into the Cartesian equation of the plane. And denominator, obviously just the length of my normal vector, which has these components. And this is the formula for the distance. This is a formula from a distance. It's a formula for the distance from a point, any point, to the plane, which is given in the Cartesian form. You don't have to do all of this work every time. Now you have just analytical formula for this thing. Of course, subject to the correction, which was suggested. We have to put the absolute value. And that's the analytical formula for the distance from the point to a plane. Now we can use this formula for this particular example. So all we have to do, extra work which we have to do before we can apply this formula, all we have to do, we have to find the point normal or Cartesian equation of this plane. And now we can do this very quickly, because all we have to do, we have to take a cross product of these two vectors, because the cross product of these two will deliver me the normal straight away. Here's the cross product. Right, the second row here is the components of this vector. The last row here is the components of the second vector. If I go for this cross product, I component is this little minor, which is a diagonal matrix for which the determinant is the product of the elements on the diagonal. So it's 2. J component, it's 1 times this 2, so it's -2. And K component, this is this little minor. You have to just multiply across this diagonal, which is 1, and that's why this component is 1. So your Cartesian equation of the plane, or point normal form of your plane, here it is. 2 is this 2. X take 2, it's this 2 component. Then goes 2, y takes 0, that's for 0, and this 2 came, -2 came from here. And z takes 0 equals, that's a point normal, or basically the Cartesian equation of your plane. You can, of course, expand everything, which will give you this. Now, to find a distance, all you have to do, you have to take this equation. You have to plug this point into your equation and divide by the length of the n vector we just found. So the distance will be, that's my distance, 2 times x, that's, well, it's all here, 2, -2, and 1 here, that's the components here, x, y, z, all in place, -4, and that's the length of your normal vector. Lucky me, this time I have to put, of course, the absolute value around here, but this time the expression in the numerator is positive, so technically speaking, everything is correct. 2 plus 4 is 6, plus 3, it's 9, take 4, it's 5, and it's 3 at the bottom. Why did I say 1 then? It's a typo then.